这下面在哪里找个声音大一点？哎，看听不到声音了。你朋友控制声音。那是这个调的。
Okay, let's get started. So where did we leave off last time? So we're dealing with sort of the equations we're going to use to describe.
声音还蛮小啊。
So we're going to use these equations to describe neurons in some large network.
Excuse me, Professor.
Yeah.
Can you speak louder?
Oh, okay. Let me.
Okay. Yeah. Since the voice is not so good.
Let me turn up my microphone. Shoot. Where did Zoom go?
就看那个Zoom 的你设置里面有没有那个音频的那个？
有是有的。
Hold on. Is this okay? Or microphone? Okay, is this okay? Is loud enough?
Okay. Yeah, it's better now.
Okay. So if I start talking too quietly, remind me and I'll speak up. Okay. So this is our starting point. So V sub I, remember, is voltage on neuron I. Okay. And what we want to know is the firing rate of this neuron, given the firing rates of all the other neurons in the network. So let's make sure we understand these equations. So the voltage relaxes back to some, oops, where's my hand go? Okay. So it relaxes back to the epsilon sum L is reversal, is a resting memory potential about minus 65 millivolts in the absence of input. But the input here, and here, the first one is the excitatory, top one is the excitatory input that causes the memory potential to go up. Inhibitory input causes the memory potential to go down. And normally, and this GJFT term is basically a bunch of fluctuating. Boy, and it's not working. GJ is a bunch of fluctuating. It basically every time there's a spike on the bottom. What I've shown here, these things are spike times. Each black mark is the spike time, And when the neuron spikes, GJ increases by a small amount and then decays again. That's the red lines. And the area under, for a particular spike, the area is just 1. And that's very convenient, as we saw, because then the average value of the GJ is replaced by the firing rate. So what happens to the voltage when it's getting this fluctuating input? So we'll plot on this axis, we'll put time. On this axis, put VI. Here is E rest, E leak, the resting memory potential, and this is E threshold, the threshold for a spike. So it starts here. If the input were completely constant, then it would just go up, generate a spike, and come back down. Go up, generate a spike, and come back down. Okay. And what we calculated earlier was T spike. The time between spikes, which I'll write down in a second. And the firing rate was basically, so the firing rate of the neuron, nu I, is equal to 1 over T spike. Okay, and what we really want to get is a sense of how big the firing rate is as a function of the firing rates of the other neurons in the network. Okay, and the key observation is that first is that WIJE, if you remember, was approximately equal to the size of tau, the membrane time constant. Tau is the same tau that appears in front of our equations, times the size of an EPSP. Okay, and obviously there's going to be a lot of variation from one neuron to the next, but this is sort of the average value. So different weights are going to have different VPSPs, and this thing was on the order of 0.5 millivolts on average. So PSPs have a big range. They can be much smaller, much larger. In humans, they can be up to 10 or 15 millivolts. A little bit smaller in mice. In turtles, they're really big, but it's on the order of that order. And then WIJ I is approximately equal to tau of the IPSP, inhibitory postsynaptic potential. And we're going to actually set that equal to tau, some scaled version of the VEPSP. Okay. So what we're going to do now is time average the input. So GJ is some, it's really fluctuates by a lot. But we can actually ask about time average, and so we're going to do the time average of. So if this is the time average, and that is just equal to firing rate of neuron J. Okay, we saw that last time. So as a first pass, we're going to replace these fluctuating time-dependent terms by just firing rates and get an intuition for, get an estimate of what the firing rate of our neuron is going to be. And when we put fluctuations back in, what's going to happen is instead of smooth things, when we put fluctuations back in, we're going to get sort of something like that. And that could make the neuron fire a little bit earlier, or it can make the fluctuations are different, maybe fire a little bit later. So the fluctuations are going to modify the spike times up or down, but they won't necessarily have a huge effect on the firing. Okay, so that's the plan. And so what we saw last time is that, let me see, next page. What we found is that the firing rate of our neuron, nu I, equaled 1 over tau and then 1 over minus log 1 minus delta E, I'll tell you what that is in a second, delta E divided by, basically it was divided by this constant here. Oh, my hand isn't working. Divided by, oops. Okay. Divided by this time average term here. Okay. And that time average term, which we called C, says C is going to be basically equal to the weights, which is tau V PSP, E PSP, times K, which is average number of connections per neuron, number of connections, and then the firing rate of excitatory firing rate, average excitatory firing rate, minus G times the average inhibitory firing rate. Okay. So nu I, and 1 over tau is a big number, right? Tau is 10 milliseconds. So this thing is about 100 hertz. So we have nu I is kind of a big number. It's 100 hertz divided by minus log of 1 minus delta E. Now we put all this stuff in. Tau V EPSP, K nu E minus G nu I. Okay, and remember delta E is this distance. It's a distance from leak to threshold. Okay, and we're going to define this ratio here, this ratio of delta E, which is in millivolts, versus V EPSB. This is going to be N, oops. This quantity here is N threshold. And what it is, the way you interpret it is a number of PSPs the neuron has to receive, the number of excitatory PSPs to get to threshold. Okay, and this is around 30. So this distance from here, this delta E, E leak is about, so E leak is about minus 65, E threshold is about minus 50. So delta E is around 15 millivolts. Remember, EPSP is about half a millivolt, so this is about 30, okay? But K is about 1,000. So tau is 10 milliseconds, K is K is equal to, is about 1,000. So 10 milliseconds is 0.01 seconds. So in units of hertz, what we end up getting is nu I equals 100 hertz divided by minus log of 1 minus N threshold, which is delta E over VPSB. Tau times K is about 10. 10 nu E minus G nu I. Okay, so this is the difference in firing rate, excitatory minus inhibitory firing rate. And the G takes into account the fact that VPSPs may be different sizes for E and I. Okay. And if this quantity here is small, so if this quantity here is small, we can use the fact that log of 1 minus epsilon is approximately equal to minus epsilon. And this thing is approximately equal to 100 hertz, again, divided by NTH over 10, nu E 1 over nu E minus G nu I. Okay. So basically, we work everything out. NTH is about 30. This 10 here, it ends up being approximately equal to 30 nu E minus G nu I. Okay. So the firing rate of our neuron is very sensitive to the firing rates of the presynaptic neurons. It's a factor of 30. So if nu E is 1 hertz and nu I is 0, the firing rate of our neuron is going to be about 30 hertz. And if nu I is 10 hertz and nu E is 10 hertz and nu I is 0, our firing rate will be 300. Okay, so it's a very, very steep curve. And it looks something like this. So if we plot on this axis nu E minus G nu I, as soon as that gets above some threshold, this goes up really fast. Okay, the firing rate of our neuron. Now, okay, so this is the version when, so this is really important. So first of all, this is, it quickly reaches about 100 hertz. When this quantity is around, this is, I don't know, but somewhere, we can actually work it out. So basically this kicks in when nu E, so NTH over 10, in threshold over 10 is about 3. So this kicks in when nu E minus G nu I is around 3. So this is around 3. And by the time it gets to 6, this is around 100 hertz. Okay. So it goes up really, really rapidly. Now let's go back to the picture we had. So the picture we have, so what about in this region? So if you look in this version where we've time averaged the input below 3 hertz. So down here, our neuron doesn't fire at all, okay? And that corresponds to situation, which go back to the previous slide. Well, it's actually right here. Right now this is time, and this is VI. So we start here at E leak, and we go up here, and this is E threshold. And in this region here, it basically, if there's no if we've time averaged the input, we just go up and we never make it to here, okay? So this is in the regime right here, where nu E minus nu I is too small to make the neuron fire. But of course, in reality, there are always fluctuations, okay? So the actual voltage is going like this, and the neuron will fire from fluctuations. So fluctuations is going to take this curve. All it's going to do is it's going to take this curve and smooth it out. Okay. So this is the actual firing rate. Oops. This is the actual firing rate. At high firing rates, you don't really notice. At low firing rates, what happens is where the time average prediction is going to say that the neuron doesn't fire. In fact, the neuron does fire. Okay. And so in the end, what we can do is we can now sort of write down an approximate equation for the firing rates of these neurons as a function of its input. And what we know is that so nu I equals some function. It was a complicated function we wrote down. Yes. So the black curve. So this black curve here. So we know exactly. Oops. We know exactly what a functional form for the black curve. We don't know a functional form for the red curve. Okay. But all we know is it looks kind of like the black curve, except at low firing rates. So instead of trying to work it out analytically, we'll just call it phi. It's some function, but what we know that it depends on is, oops, it depends on nu E minus G nu I. Okay. Okay, so that's all this analysis just tells us this, right? Depends on, in some ways, we almost could have guessed this from the beginning. The higher the excitatory firing rate, the higher the average excitatory firing rate, the faster our neuron's going to be firing, and the higher the inhibitory firing rate, the slower our neuron's going to be firing. Now, this, of course, is equilibrium firing rate. So we're going to do something that is a bit tacky if you're a mathematician, but physicists do this stuff all the time, is we kind of make up equations. We're going to write this. So tau d nu I dt equals this phi minus nu I. Okay? So this is an approximation. Okay, it's just a made-up equation. It should probably be good when nu I is close to 5. But what it tells us is, if this is bigger than nu I, then the firing rate is going to increase. If it's small, the firing rate decreases. Okay, and in equilibrium, we get what we had before. We get nu I equals phi. So the equilibrium value is correct. And we just added some dynamics to tell us that if phi is, higher than our current firing rate, I mean, you can imagine we put our neuron in, and all of a sudden it's not firing at all. We connect it up, it's going to start firing. Firing rate's going to go up. And dynamics just tells us what happens. Okay. So now we're going to do one more thing. And that is this G function here, this G quantity. G, remember, just to remind you, is it back here? Yeah, G is the ratio of excitatory inhibitory PSP size, okay? It just tells us that, the inhibitory PSPs are G times larger than excitatory PSPs, or G times smaller, depending on the sign of G. But G may depend on whether or not the postsynaptic neuron I is excitatory or inhibitory. So we're going to actually do this. We're going to put an E here and a GE. And this is going to turn out to be very important. Tau E, tau I, d nu I dt equals phi of nu E minus GI nu I minus nu I. And we might as well, we can let these be different as well. Okay. And all it says is that the ratio of excitatory inhibitory PSPs onto excitatory neurons may be different from the ratio of excitatory to inhibitory PSPs onto inhibitory neurons. Okay. It turns out if we don't make that assumption, things do not work out. Okay, so just to remind you, we started with sort of a relatively simple equation, the thing on the top in the magenta box. It's just a linear integrating fire neuron that gets input from the other neurons of the network in a current-based model. And what that does is, you know, if it gets enough excitation, the firing rate goes up, it hits threshold and spikes and comes back down, up hits threshold, spikes and comes back down. The black marks, so the black curves are what happens when there are no fluctuations. It's very smooth. And the red curves are what happens when there are fluctuations. We worked out the firing rate when there are no fluctuations. We've time averaged this G. Okay, we time averaged this G. We went from the red curve to the blue line. And we could work out the firing rate analytically in that case. And we got a picture like, oops. Oh, where is it? We got a picture like this, the red curve. So the red curve is, or actually the black curve is our analytic expression for firing rate when the input is constant, but we know that's not right. Okay, we know with fluctuations, what's going to happen is you're going to get the neuron's going to fire even when it wouldn't in the time average case, and so our firing rate is this red curve, and that is what we call phi. Okay, and maybe it's different for excitatory and inhibitory neurons. And then what we did was we allow excitatory and inhibitory neurons to be different. They can have slightly different gain functions, the red curve for the excitatory and inhibitory, but they're going to kind of look like this red curve up here. And we're going to have different ratios of IPSPs to EPSPs. Okay. So what we want to do now is analyze these equations. And really the question is, what are the fixed points? What are the dynamics? What happens here? So one thing to take into account, of course, is still if we have n neurons, we have n equations, and n can be a million. But we can there's something very, very cool about this, and that is this term here doesn't depend on I. Okay? So what we're going to do is average both sides over I. Okay? I'm going to do that on the next piece of paper. So we have tau I, tau E, ddt of nu EI equals phi E. I'm not going to write its arguments, minus nu IE. Okay? And what we're going to do is basically something very simple. We're going to take this, we're going to basically average, actually, I'm going to put my DDT over here. So I have room. What we're going to do is basically average both sides. Sum on I equals 1 to n. And we're going to divide by 1 over n. Okay? We're going to do it everywhere. Sum I equals 1 to n. I don't have room, but we want to put a 1 over n in there. And 1 over n, the sum I equals 1 to n. Okay? So this quantity here is just equal to phi E. Nothing changes. Phi E doesn't depend on I. And this quantity here is nu E. This is the average firing rate by definition. This is also nu E. Average firing rate. And what that tells us is we have the equation tau E d nu E dt equals phi E of nu E minus GE nu I minus nu E. And tau I d nu I dt equals phi I of nu E minus gi nu I minus nu I. And this, of course, is an E. Okay. So these are our equations. They're the Wilson-Cowan equations. The paper is on the website, derived in 1972, I think. Although their derivation was also not very good. This is kind of a made-up derivation, right? I'm going to put a little rigor into this a little later, but if you do a huge amount of work, you end up getting this equation change. So it's a pretty good description of what's going on. And you know, there are various versions of this. Sometimes there's no minus sign. It doesn't really matter. But this is the idea. So we now have two equations, two dynamical equations, and we want to understand the behavior of these dynamics. Okay. So given these equations, what happens? Okay, what are the equilibrium? What are the firing rates? Do we get anything sensible? And it turns out the behavior of these equations is surprisingly complicated. Okay. So as a warm-up, what we're going to do is consider it's a warm-up. So warm-up. So an all excitatory network. And we'll just set, what that means is we'll set nu I equal to 0. So our equations become tau E d nu E dt equals phi E of nu E. Actually, I'm going to set nu E I equal to, instead of setting it to 0, I'm going to set it to some fixed value, nu I 0. So we don't allow it to change, but it can be some non-zero value. Okay, minus nu E. And so how do we solve this equation? Well, the first thing we ask for are what are the equilibria? So whenever you have a differential equation, if possible, you find the equilibria, the stationary points of the equation. So equilibria is when d nu E dt equals 0. And at that point, of course, basically nu E equals phi E. Okay. So what we want, and the way we find that is basically graphical. It's kind of cool because it gives you very powerful, gives you something very powerful. So on this axis, we're going to basically plot nu E. I'm going to plot on this axis phi E of nu E. I'm going to actually, I'm going to start out with nu E I. So I'm going to start out with nu I 0 equals 0. And so we know the shape of this thing, right? It goes up, you know, it's mainly, and then it shoots up really fast and goes up, okay? So that's phi E. We can also plot on the same axis, we can plot just nu E, right? So this is phi E, and this is just nu E. Nu E versus nu E, it's a 45-degree line. And this is phi E. Okay. So where the equilibria occur? Equilibria occur. So this is an equilibrium, very close to 0. That's an equilibrium. and that's an equilibrium. Okay. Shoot. So there are 3 equilibria. Okay. So that tells us the fixed points. So this one is close to 0. This one is some finite value. That one is of high firing rate. So this one we know. Oops. So we know this one is going to be on the order of, 100 hertz, maybe 200 hertz, maybe 50 hertz, but pretty big. Okay. These 2 are going to be small, and so and what we expect just intuitively is that this one here will be stable, that will be stable, and all that says is the stable one down here is saying if the network is barely firing, it's not going to fire. Up here, if it's firing like mad, the recurrent connectivity is going to keep it firing, and this one should be unstable. Okay, so this is our intuition. If you spend a lot of time with ODs, you'll have the same intuition. If not, you won't, but that's okay. What we want to do is sort of put a little mathematical teeth into that and figure out, what really the equilibrium are. So what we're going to do is linearize around a fixed point. Okay, so we're going to call this these things. This is nu E0 is a firing rate at a fixed point. It could be any one of the fixed points, that one, or that one. And we're going to let nu E equals nu E0 plus delta nu. And we're going to ask about dynamics of delta nu. Okay. Now nu E0 is a constant, so our differential equation becomes tau E d delta nu dt equals phi E of nu E0 plus delta nu minus G nu I0 minus nu E0 minus delta nu. Okay, so this equation is exact, not very useful. What we do now is Taylor expand this quantity here. So this thing here is approximately equal to phi E of nu E0 minus G nu I0 plus partial of phi E with respect to nu E0 times delta nu. Okay, that's the first order Taylor expansion. And the nice thing is that here's green, got the worst colors here. And the nice thing is that this term here cancels this term here. Okay, these 2 terms are equal because by definition, that's the definition of an equilibrium. When nu equals E0 equals phi of phi E of nu E0. Okay, and we do that, we get a differential equation. Tau E d delta nu E dt equals a partial of phi E with respect to nu E0 times delta nu, oops, call it delta nu E minus delta nu E equals partial of phi E with respect to nu E0 minus 1 times delta nu E. Okay. So if this quantity here, so that what this means is that delta nu E equals delta nu E0 at time t equals 0 times exp of t times partial of phi e with respect to nu e0 minus 1. Okay, that's a solution. So the sign of this is super important. So positive, unstable, fixed point. Negative, stable fixed point. Okay. Let's go back and put these here. Okay. And so if we go, so basically this quantity here, this here is the slope of gain function of phi e. And if the slope of phi is greater than 1, the fixed point is unstable. If it's less than 1, the fixed point is stable. Okay. So if you look here, here the slope is positive. So this kind is going to be unstable. Okay. Here the slope is sorry, it's not positive. The slope is greater than 1. That's an unstable fixed point, as we suspected. And over here, the slope is less than 1. So these are going to be stable. Okay. And another kind of important way to see this is the dynamics is, if you look over here, it's phi e minus nu e. Okay. So in this region here, phi e is greater than nu e, which means the firing rate tends to increase. So the firing rate tends to go to the right. Over here, phi e is less than nu e, and now you're pushed to the left. Okay. So in this region, you're pushed to the left. In this region, you're pushed to the right. In this region, you're pushed to the left. Okay. So these blue arrows are going to be actually super important in the more complicated case. Okay. So the key take-home message for these all excitatory networks, besides you have sort of these 3 fixed points, 2 are stable, 1 is unstable, is that we can analyze this graphically. We can draw pictures, and those pictures are going to tell us something about the dynamics. Okay. So I think this is a good time for a break. What I'm going to do, so I'm going to come back 5 minutes. You guys can hopefully you'll absorb this in the next 5 minutes, and then we're going to take the case. We're going to consider the case of both excitatory and inhibitory neurons, which is a bit harder. But again, we're going to draw pictures and use geometry, and hopefully it'll be reasonably straightforward. In the meantime, if you have any questions, feel free to ask. So we'll take a 5-minute break. Okay, so let's now go back to our two-dimensional equations, look excitatory and inhibitory neurons instead of just excitatory neurons. Let me cut. Oops. Okay. So those are the equations we're going to be using. And so in the case of one-dimensional, so by the way, I should point out that if we change the inhibitory firing rate in this version, okay, so that basically, so this was the case where inhibitory firing rate was 0. If we change it here, increase it, all this does is shift this curve to the left or the right. So it doesn't change much. Okay, it moves fixed points around, but again, we get a stable one, unstable one. If you move it far enough in one direction, the stable ones can disappear, fixed points can disappear, and that's going to be important later, but really it doesn't do very much. Okay. Okay, so back to this. In the previous example, we found the fixed points, right? These 3 red points are the fixed points. We can do the same thing here, but you'll notice that in fact, each of these equations, we can, the fixed points are, so again, we actually are going to look at fixed points. So the fixed points, which we really care about, are d nu edt equals 0 and d nu idt. Okay. If both of those are satisfied, those satisfied at a single set of points. But notice that d nu edt equals 0. This gives you a line or curve. There's a whole curve along which d nu edt equals 0, and there's a whole curve along which d nu idt equals 0. And those curves are called, so these curves, so curve along which d nu e dt equals 0, it's called a nullcline. Called a nullcline. And that's, in that case, it's the excitatory nullcline. The curve along which d nu I dt equals 0 is called the inhibitory nullcline. So what we're going to do is find those nullclines and then look at the intersections. The intersections give us the fixed points, but the nullclines give us lots of information about the dynamics. Okay? So we're going to basically find these nullclines one at a time. We're going to start with the inhibitory nullcline. I'm going to start with the inhibitory nullcline because it's easier. And then we'll work on the excitatory nullcline. Okay, so that's the procedure. We're going to find these curves along which the d nu e dt or d nu I dt is 0. The intersections will give us the fixed points, and the curves will help us analyze the stability of those fixed points. And that'll tell us really everything we need to know about randomly connected networks like excitatory and inhibitory networks, which is kind of cool. Okay, so d nu I dt equals 0. Equals 0 implies nu I equals phi of nu e phi I of nu e minus gi nu I. Oops. Gi nu I. Okay. So what we're going to do, I mean, this is a nonlinear equation, but what we can do is we can fix nu e and find the value of nu I that satisfies this equation. We'll do this over and over again. That'll be a little more clear in a second. So in this axis, we're going to plot phi I versus nu I. Again, we're going to look at the intersection of the 45-degree line. I'm going to plot this for different values of nu e. I'm going to put it over here. So this is a nu e nu I plane. And okay, so what we do is, let's say nu e equals 0. If nu e equals 0 and nu I equals 0, that means that none of the other neurons in the network are firing. Okay? And the classic view, I'm going to write this down because it's a classic view. Neurons don't fire if they don't get input. Don't fire if they don't get input. If they don't get input. Okay, so remember this is a classic view. It's going to turn out to be wrong, but it's what people generally thought for a long time. So what that means is if nu equals 0, the nu equals 0 curve, phi I is basically 0. So this is nu equals 0. Okay, and what that means is that the point nu I equals 0, nu e equals 0 is part of the inhibitory nullcline. So that's a point here. So now we increase nu I. So this is nu I. I don't know, we can put in some numbers. This is nu I. So this is nu I equals, say, 1 hertz. Equals, I don't know, 1 hertz, which maybe is right here. And now, phi I, now we have an intersection, right? This is now, if nu e is, I don't know, 1 hertz maybe is too high. If nu e is goes up a little bit, now we're going to see basically if nu I is 0, the neuron's firing at some rate. As nu I increases, this goes down. So the red curve, we're just plotting the gain function. This is nu I versus, or phi I versus nu I at different values of nu e. So that's going to be a point, somewhere over here. Actually, sorry. So if this is 1 hertz, 1 hertz, then basically this is, I don't know, it might be 10 hertz. This is the firing rate of the inhibitory neurocline. So that's a point on the nullcline. This point satisfies the equilibrium condition d nu I dt equals 0. As you increase, so nu I gets bigger, what happens is this just moves up. Okay, I don't know, it goes in some direction. So what this tells us, so this is the, call it the I nullcline. Okay, and this has a nice interpretation. The larger the excitatory firing rates, so what we're doing really with the I nullcline is we're fixing the excitatory firing rates and asking, what's equilibrium value of inhibitory firing rates? The higher the excitatory firing rates, the more input the neurons are getting, and so it takes more inhibition to satisfy this equality here. Okay, the bigger nu E is here, the bigger nu I is going to be here. Okay, that's all it says. There's also something very important about this, and that is dynamics. Okay. So if you fix the excitatory firing rate, so remember, go back here, d nu I dt is the difference between phi I and nu I. So if nu I is really small, this is going to be positive. If nu I is really big, it's going to be negative. Okay. And what that means on this, if you go back to this curve, is the dynamics is in this direction. Oops. So dynamics is in this direction and this direction. I'm going to erase this thing. Okay. So these red curves, which are these red arrows, which are magenta arrows, which are going to end up being very important, tell you what happens at fixed excitatory firing rate. So if you fix excitatory firing rate to this value and start here at this point, the inhibitory firing rate is going to go up. d nu I dt is positive down here, it's negative up here. Positive on the bottom, negative on the top. Okay. So that's the excitatory nullcline, inhibitory nullcline. That was pretty easy. The excitatory nullcline is much more interesting. Okay. So again, we're going to put, so down here, again, we're going to put phi E versus nu E. Different values of nu I. Up here, we're going to put nu E and nu I. Okay. And we're going to see the same sort of thing we saw before. This is our 45-degree line. Okay. And we're going to plot, phi. So this is just the nu E. This is nu E equals nu E. Okay. And now what we're going to do is plot different values of phi E. Actually, let's go back. System color scheme. Okay. So this is our 45-degree line. And now what we're going to do is plot phi E for different values of nu E, for different values of nu I. So this is nu I equals 0. This is what curve we saw before. This is nu I equals 0. Nu I equals 0, okay? And so these 3 points, this point here, oops, this point here, this point here, and this point here are all on the excitatory nullcline, okay? These 3 dots, when nu I equals 0, are the values at which the excitatory neurons are in equilibrium. This is exactly what we saw before, right? If it's not firing at all, they won't fire. Sometimes it's an all excitatory network. If they are firing, they will. If they're firing at high rate, they'll fire, and in between is an unstable equilibrium. Now, this is what happens when we increase nu I. So increase nu I. So nu I increases. Okay, so now so this is a larger nu I, let's say right here. So this point here is still in equilibrium, right? 0 firing rate. This point here is moved over a little bit. So this point here is now here. This point here is now here. Okay, and you can see as you increase nu I, these points just move over, and we end up getting a curve that looks like this. Okay, and one that goes up here. So it's got this, so, you know, we don't really know the sort of the values. We know this is out here, this in the order of 100 hertz. Presumably this is, I don't know, this height is probably about 100 hertz. So we don't really know, but we know it has this generic shape. Okay. It's got this point here, this line here on the 0 axis, indicating that if you don't, if you don't get any excitatory input, you're not going to fire, and adding inhibitory input is not going to make you fire. And then out here, there's this regime where, out here is this sort of this, on this branch, your firing rate's really high. So over here. So in this branch, your firing rate is really high. Oops. Here we go. This branch, your firing rate is really high. Okay. And that should be stable. And over here, your firing rate is intermediate value, but that should be unstable. And again, if you look at the equations, okay, the excitatory firing rate is the difference, the sign of d nu e dt, the dynamics, is determined by this difference, okay? If phi is greater than nu e, then d nu e dt is positive. If it's less, d nu e dt is negative, okay? So going back to here, we can now draw sort of dynamics. So here, we're pushed to the left. This is stable fixed point. In here to the right, and here to the left, okay? And, it's kind of easy to draw these arrows because we know the arrows, d nu e dt is 0. So along the nullclines, on these points, d nu e dt equals 0. So it's got to be positive on one side and negative on the other side. And it's kind of really easy to see what's positive and what's negative. If you go way out here, nu e is really big, it's going to be negative, right? As nu e goes to infinity, and that means on this side of the curve, it's got to be negative everything. Okay. So we can now combine our excitatory and inhibitory nullclines, right? So this is excitatory one. That's excitatory. This is inhibitory. And we don't really know much about the details, but we know about the generic shapes. Okay. And so we can now, oops. So we now combine them on the same graph. This is nu E. This is nu I. We're going to use blue for excitatory. It's blue. Yeah. So blue for excitatory, it's all along here. And then it starts over here. We don't really know. It's got some shape like this. And red for inhibitory. Now, and the intersections are stable fixed points, okay? So I don't know what the red looks like, but it looks maybe something like this. We have a lot of freedom where we could draw it, right? We could draw it over here. So these are all possible nullclines, okay? So these are possible inhibitory nullclines. So oops. Oh, I know what's happening. So possible I nullclines. Okay. We don't know which one it is, right? Depends on the details. But what we know about, if it's this one here, right? The only fixed point is at 0. The network is just dead silent. So that's not likely what we're going to see in the brain. So we can kind of rule this one out. That one goes away. And, you know, so these two are both possible, right? Here, this one has equilibria at non-zero values. So does this one. So they're both potential nullclines. We're going to focus on the one in the middle. Okay. So we're going to basically focus on that nullcline. There we go. And it has fixed points here, here, and here. We want to know the stability of those fixed points. Okay. And some of them, so we know, and we can actually get that very nicely by drawing arrows. Okay, they know the arrows here are this direction, and this direction, and this direction. So these blue arrows are what happens to the excitatory firing rate at fixed inhibitory firing rate. And the red arrows is what happens to the dynamics of the inhibitory firing rates at fixed excitation. And now at any particular point, here, the actual dynamics is a combination of the blue and the red arrows. So for instance, if our starting point is right here, what happens? Okay. Let's try orange. Okay, if we start here, we're going to move to the right and up. Okay. As we get closer and closer to the blue point, to the blue curve, let's try that again. As we get closer to the blue curve, the actual d nu EDT at the blue curve is 0, right? On the blue curve, the nu EDT is 0. So the trajectories, so the orange is a trajectory. At this blue nullcline, on the blue nullcline, the trajectory is basically completely horizontal, vertical, okay? And now as we go above, we get pulled over to the right, and over here it's horizontal, and we go, okay? And you can sort of just tell from that this is stable. This one over here is also stable, right? We get pulled to the right. We're over here, we get pulled to the right and down, and in we go. That's a stable fixed point. You can just get that from the arrows, which I drew. Actually, let's. This error is wrong. What's happening here? Oh. So this error should be to the left. Dynamic system at that point. So if you start here, you just get pulled directly down in there. So that's clearly a fixed point, stable fixed point. So what about the intermediate fixed point? If you start here, you're pulled to the right and up, okay? But, and this one you don't know, right? Wait, hold on a second. You pull to the right and up, but you know, once you get to here, you actually, so this is an important point. You have to cross this line, the red line you have to cross horizontally. So you can't cross, right? You get pulled up. Get pulled up, but you can't cross, so you get over here and you end up at this fixed point. You start here, you end up here. So this point here is unstable. Okay. So this picture, and this is, and what you can see is that the stable fixed points are, so here, so these are both stable. But and so in this analysis, you can have stable fixed point zerifying, right? Which is not what we see in the brain. If you stick an electrode in the brain anywhere, you'll see neurons are firing. You know, stable fixed point at a relatively high firing rate. You can try to actually, so the second one is, so sort of the potentially interesting stable fixed point is this one, okay? That might be intermediate firing rate, but that's kind of high firing rate, right? It's also a fine tuning issue. You have to basically carefully place the inhibitory nullcline to get a reasonably high firing rate, okay? And this one and the intermediate one here, this one here is unstable, okay? Unstable fixed point. So in this simple classical picture, so what do we see in the brain? So one possibility, of course, is the nullcline, the actual nullcline you see in the brain looks like this. So it could be that the inhibitory nullcline looks like this, and you have equilibrium at a very high firing rate. But that's around 100 hertz, and that's not observed in the brain. It's just too energetically expensive. Neurons would die at that firing rate. What you see are firing rates of a few hertz, 2, 3, 4 hertz, okay? So to get to these low firing rate equilibrium, this picture, something has to be wrong with this picture, okay? There's a massive fine tuning problem. Any small fluctuations are going to drive you to really high firing rate or to a situation where you crash and the neurons all become quiet. And the thing that was wrong with this picture is this classic view. Okay, classic view is that neurons don't fire if they don't get input. And let's see what happens when we drop that. Okay, and we're going to go back to the construction of the excitatory nullcline, and I'm going to actually redraw it here. But what that means is when nu equals 0, the gain functions. So I drew them. So right now I drew them. The gain functions like this. Oops. So I drew the gain functions when nu equals 0, starting down here at 0 and going up. Okay. If we draw this assumption, what that means is even when nu equals 0, when a neuron is getting no input, excitatory input whatsoever, it still fires. And so what that means is the nullclines actually go like that. Okay. So let's redo this analysis with the different nullclines. So it's sort of the same set of curves. Oops. This is nu E, nu I. And down here, we're going to have nu E, phi E. Okay. Try this a little better. They line up. Nu E, phi E. Again, we put the 45-degree line. And what we do is we plot phi E as a function of nu E when nu I equals 0. And what we get is a curve that goes like this. Okay. So this is nu I equals 0 curve. And we get a point on the nullcline right. So what this says now is there is no equilibrium when none of the neurons are firing. Because when none of the neurons are firing, the neurons will be, some neurons at least will be spontaneously active. Okay, this is a very different view of the brain. Now we increase nu I and this gets pulled down, something like this. So higher nu I, this is nu I greater than 0. We get maybe some point here. We get a point here in the nullcline. And eventually, so this is nu I, oops. The nu I larger. Eventually we get now a fixed point right here. Okay. And now if we make nu I even larger, you get other fixed points that occur like this. And so what you end up getting is a picture like that. Okay. This point here appears as soon as you get this crossing right here. So the inhibition gets large enough, a fixed point appears. And this actually has a lot of intuition. Okay. If inhibition is 0, right? You've lost a fixed point at 0 firing rate. All it can do is fire at really high rates. Okay. If inhibition has some intermediate value, now you can have the neurons fire at low rate, not enough for the recurrent excitation to take over, or high rate, and in between is an unstable fixed point. Okay. And if there's way too much inhibition, as in over here, all you can do is fire at low rate. So this should be a fairly intuitive picture. And again, the arrows are to the right here. Oops. The arrows are to the right here and to the left here. Okay. And now we can add in, we can just take this picture, add in the inhibitory nullcline, which now has some shape. Okay, maybe not quite to scale. Again, the arrows go like this. This is I nullcline. Okay, and now we have, this is, I mean, the way I draw it isn't necessarily so, but actually let's draw sort of a more realistic picture of what these actually look like in real life. So it turns out that the E nullcline really comes down, hugs this point, and starts sort of going up here. Shoot. Down here. Drawing is not my strong suit. Goes up here. Then something like this. And the inhibitory nullcline now can go like this. And you can have a nice low firing rate. Rate equilibrium. Okay. And that could be sort of as low as you want. And it's also very stable. So if you go back to this set of nullclines, right, you have this fixed point at 0, right? So this is a very dangerous fixed point to have in a network because if all those neurons stop firing, you die. Here, that can't happen. Okay. There's only one equilibrium. It may or may not be stable, but there's only one. So you don't have to worry about crashing to 0 and die. Okay, and we should put in the dynamics. The arrows go in that direction, and then the salutary ones go this way. And what we want to do now is examine the stability of this fixed point. Is that stable or so? Stable or unstable? Stable or unstable? Or unstable? Okay. And we have about 10 minutes, which should be enough. Okay, we're going to use, well, 8 minutes. We're going to use the exact same procedure we did before. So if you go back to our equations, actually, I think I will, I may have, go back. Still there. Okay. So equations are still there. What we're going to do is let we'll let nu E go to nu E0 plus delta nu E, and nu I go to nu I0 plus delta nu I. Okay. And so we're going to write down differential equations for delta nu E and delta nu I. I'll do delta nu E in detail. So tau E d delta nu E dt equals phi E of nu E0 minus GE nu I0 plus delta nu E minus GE delta nu I minus nu E0 minus delta nu E. So delta nu E0 and nu I0 fixed point. So first of all, it's approximately equal to phi E of nu E0 minus GE nu I0 plus, and then going to subtract off nu E0 there, plus phi E prime, oops, phi E prime, evaluated nu E0 minus GE nu I0 times delta nu E minus GE delta nu I, and then minus delta nu E. And as usual, these two terms cancel, right? That term and that term are the same. That's what it means to be in equilibrium. So this is equal to, I'll just call it phi E prime. I'll write the arguments times delta nu E. So minus 1 times delta nu E minus phi E prime GE delta nu I. Okay. So that's the differential equation for delta nu e. The one for delta nu I is about the same. Tau I d delta nu I dt equals phi I prime phi I prime delta nu e minus phi I prime plus 1 gi delta nu I. Okay, so tau e d delta nu e dt, oops. Tau I. Okay, so these are linearized differential equations. Copy onto, oops. I'll copy these onto the next page. And then write them in matrix form. Okay, so ddt of delta nu e delta nu I is equal to phi e prime minus 1 minus phi e prime ge phi I prime and minus phi I prime plus 1 gi. Oops. The gi is in the wrong place here. This is phi I, oops, I prime gi plus 1 delta nu I. So minus phi I prime plus 1 gi plus 1 delta nu I. Okay. Oops. Okay, shoot. Didn't leave myself enough room. So we have phi e prime ge, and we have minus phi I prime gi plus 1, and that gets multiplied by delta nu e delta nu I, and we have to divide these by tau e, and these by tau e, this by tau I, and that's by tau I. Okay. So this is the set of equations we want to solve. We want to find the fixed points. So this is something that you guys should definitely know. Actually, I'm going to go to another page. So this is, I'm just going to write matrix equation tau dx dt. So this is a math aside. Actually, I'll do the, well, we can, 3 minutes. I'll start this and you guys see if you know this. Equals a dot x. Actually, I wrote this down the other day. So I'll focus on 2D matrix. So we have d dt of del nu e del nu I. We have some coefficients a, b, c, d, del nu e del nu I. Del nu I. So we're basically out of, well, we're almost out of time. So this has a solution of del nu e del nu I is equal to del nu e 0, del nu I 0, e to lambda t. So d dt of e to lambda t just brings out a factor of lambda. Okay, so when we plug this in, we get lambda del nu e 0, del nu I 0, e to lambda t equals a, b, c, d, del nu e 0, del nu I 0, and in here is an e to lambda t. Which goes in here, and the e to lambda t's cancel. So basically, we just have a matrix equation. We're out of time. I'll stop here. I'm going to finish up with this. What we're going to do is we want to know that whether the real part of lambda is positive or negative, because that tells us about stability. And we're going to find a very simple expression for lambda in terms of a, b, c, and d. And then we're going to go back, and these basically are our a, b, c's, and d's. I'm going to find stability of our fixed point. Okay. So I will end there. And as usual, in a couple hours, possibly this evening, everything will be, all this will be on the website. Okay, thank you.
Thank you. Any question?
A lot of questions.
Yeah. Yeah, you can ask question now. Yeah.
I didn't join the last lesson. So I will actually if you will ask you on the next lesson.
Excuse me, Professor. Yeah, I have one question.
Oh, sure.
Yeah, when will you present the teaching notes and the video recording in your web page?
Yeah. Oh, when?
When? Yeah.
So it should take, the notes I can do quickly. A bunch of meetings now. So the for notes from last week should be on the webpage, right? From 2 days ago. They're on the webpage. Yeah. It takes a couple hours to make the video.
Okay.
But I'm super busy today, so certainly by tomorrow morning, it'll all be there.
Okay. Okay.
Maybe earlier.
Okay. Thank you.
Sure.
Thank you.
Bye.
Yeah, I think the student will ask your the questions next week. Okay.
Yeah, yeah.
So we
Definitely.
can stop here.
Yeah. And if you have any
Okay.
questions, feel free to email.
Okay. Yeah.
Okay.
You can also write email. Okay. Bye.
Okay. Bye.